Hello folks, we come to the part 3 video of this exercise 5.2 and here we are supposed to find the derivative of cos root x. Let's start right away by assuming y as cos root x. Let y be equal to cos root x. We will make a substitution here so that things become simple. We could have u as root x and that converts y as cos u. Now we can have their derivatives. U is in terms of x, so du by dx. We have learned earlier that x raised to half has got the derivative 1 by 2 root x. So this will come and comes by the formula nx raised to n minus 1. That's how we get it. Y is quite simple in terms of u, so dy by du. Cos, we know the derivative is minus sin u. So putting this together, dy by dx, we are going to use the chain rule, dy by du into du by dx. All this is ready with us, so we just need to substitute dy by du is minus sin u and du by dx is 1 by 2 root x. This is perfectly okay, but this u has to come back in terms of x and u for us is root x. So your final derivative is minus sin, what is that, root x by 2 root x. That's about it. Quite a simple function as compared to what we have done earlier. Okay, now next two problems are very important from the board point of view, has been asked many times, and it's also important from the understanding point of view. The question says that f of x, it's a modulus function. F of x is equal to modulus of x minus 1. Question says check whether it is differentiable at x equal to 1. Now there are two facets for this. Function, if we check this function, x minus 1, if you have the function like this 0, 1, this function is like this. At 1, it forms a V-shaped thing. Now what happens is when you take the derivative at 1, the derivative from left side and right side, they will vary. And when they vary, we are not able to get the derivative. Actually, this function doesn't have derivative. Now, why it doesn't have a derivative? As we had done for continuity, we are going to do here also. In the continuity, we had seen that whenever there are functions which are not so well behaved, we check the limit from the left side and we check the limit from the right side so as to ensure that they are continuous. Here also, because the function modulus greatest integer functions, these are little complicated functions. So we will check the derivative from left and the derivative from right and we'll see if they tally. If they are tallying, derivative is existing. But by chance, if the derivative from left and derivative from right, they don't tally, then the derivative will not exist. And that is what we are going to check over here. Now, the next thing that we have got to learn here is what is the definition for the left derivative and what is the definition for the right derivative. So roughly we will learn what is the left derivative and right derivative definition, then we will apply it here. Suppose you have to find the derivative of a function at a point A. There is something called as a left derivative and there is something called as a right derivative. Now this is going to be a left derivative, and left derivative by definition it is going to be limit as h goes to 0 f of a minus f of a minus h. You can check by h. And right derivative is going to be limit as h goes to 0 f of a plus h. The bigger one comes first, f of a plus h minus f of a by h. We are going to use this definition over here and that's how we are going to get the derivatives. Let's start right away. Here it is 1 for us. The point where we have to check it's 1. We have 1 minus h here. We have 1 plus h here. So right away, let's consider the left derivative. Left derivative at 1 by formula. Limit as h goes to 0. F of 1 minus f of 1 minus h by h. And let's have these things. F of 1 means wherever in the x thing you put 1. So what will it come? 1 minus 1. This is 1 minus 1. And what will come here? Same way, 1 minus h minus 1. What we are doing, we are applying the definition. Okay, f of x is this. So here it is 1. So instead of x we have put 1. Here it is 1 minus h. So instead of x we have put 1 minus h. And h is as it is. So how does this solve? Limit as h goes to 0, 1 minus 1 is 0, and here these ones are cutting, and here you have modulus of minus h. Any negative out of the modulus, when it becomes positive, we know it. So it comes to limit as h goes to 0, minus h by h. Why this has become positive, and that minus sign is already there. That way this gets cut and it becomes minus 1. So overall the left derivative formula is the value is coming as minus 1. Let's take the right derivative. And the right derivative, how does it come? Limit as h goes to 0, f of 1 plus h minus f of 1 by h. Again, let's apply the definition. We know f of x is modulus of x minus 1. So modulus of 1 minus h minus 1. Here, this we already know. It is 0. So no need to do it again. If you want, you can do it also. 1 minus 1, modulus of h is h. So what happens? H by h on cancelling gives you 1. So under limiting situations, answer is 1. Left derivative is minus 1, but right derivative is 1. They are not equal. And that is why the derivative is not existing. Left derivative at 1 is not equal to right derivative at 1. Therefore, f is not differentiable at x equal to 1. That's about it. Then we can move to greatest integer function. Now see how it is. At x equal to 1 and x equal to 2. How does that happen? F of x is greatest integer x, where x is defined between 0 and 3. And they ask us to check differentiability at 1 and at 2. So first let's like all this. Let's start with the differentiability at 1. Consider the differentiability of f at 1. That means limit as h goes to 0, f of 1 minus f of 1 minus h by h. How much does this come to? See, f of 1 means greatest integer 1. F of 1 minus h means greatest integer 1 minus h by h. Let's find this. For every integer, the greatest integer is itself. So for 1, it is going to be 1 itself. Now 1 minus h is a small value. So 1 minus h is something like 0.98 or 0.99 or something like that. If that is the case, then the greatest integer is going to be 0, because it is going to be the integer before this number. So like that, this is going to go to 0 and by h. So you're left with limit as h goes to 0, 1 by h. H is going to 0, something like 1 by 0. So that's something not defined. We don't know what's the value, but something not defined. So that's how you're getting the left limit. Now you consider the right limit. Right limit. Limit as h goes to 0. F of 1 plus h minus f of 1 by h. How much does it come to? Limit as h goes to 0. F of 1 plus h is greatest integer of 1 plus h minus greatest integer of 1 by h. 1 plus h means 1 plus some small value. It can be something like 1.1 or 1.2 or something like that. Automatically, the integer before that is 1. So greatest integer of 1 plus h is definitely going to be 1. And greatest integer of 1, because it is an integer, is 1 itself. What is coming up? Limit as h goes to 0, 0 by h. So it is 0. So something like 0. So what happens here? Left limit at 1 is not equal to right limit at 1. At one place you have infinity, other place you have 0. So if it's not differentiable at x equal to 1. Now, whether it is the same story at x equal to 2, or because because of the whether the definition is going to vary when x equal to 2, that we have to find out. So let's check at x equal to 2. Let's see what happens. Same thing. Let's consider the limit. No, sorry. We are considering the left derivative at 2. That means limit as h goes to 0, f of 2 minus f of 2 minus h by h. So what is it by definition? Greatest integer of 2 minus greatest integer of 2 minus h by h. For an integer function, greatest integer is itself. 2 minus h, as we have seen before, is 2 minus a very small quantity. So like that, it could be something like 1.98 or something like that, 1.99. Automatically, the integer before that is going to be 1. So here it is going to be 2 minus 1 by h. So how is it? limit as h goes to 0, 2 minus 1 is 1 by h. That means 1 by 0. So that goes to infinity. So same, like the case is almost same like what we did before. Now we will take the next one. Left derivative at 2. Sorry, right derivative at 2. Limit as h goes to 0, f of 2 plus h minus f of 2 by h. So limit as h goes to 0, greatest integer of 2 plus h minus greatest integer of 2 by h. Limit as h goes to 0, 2 plus h means 2 plus something, maybe something like 2.1 or 2.01 or 2.001, something like that. The integer before that is definitely 2. So this is going to be 2. For an integer point, the greatest integer is itself. So this is 2 by h. Same, the case is exactly same as before. So like 0 by h. Overall, it's going to be, in limiting conditions, it's going to be 0. What happens? Left derivative at 2 is not equal to the right derivative at 2. So f is not differentiable at x equal to 2. And that's a question. They ask us to check the differentiability at 1 and 2, and it is not. That's all about this. We are done with the part 3 video. In the next video, we come with a new exercise. Thank you.